Hello and welcome back to another video on control. Today's lecture is on the jury test for the evaluation of system stability. So the contents, I'm going to introduce you to the stability of a system in practice and also in theory. I'll then move on to the jury test where I'll introduce you again to the unit circle that we went through in the last block of lectures, and then I'll show you the process behind the jury test, so effectively determining if the system is stable. So populating the jury table, the necessary and sufficient conditions. Got two examples then to run you through, some checking and then some checking questions and a summary to finish off. So after the end of today's lecture, I hope that you can explain the method behind the jury test for the evaluation of system stability and how to go about undertaking the tests, the steps to the test, and also explain the process to determining an unknown proportional control gain value, KP, to give you a stable. On this slide, we're looking at the stability of a system in practice. So I've got here 3 examples whereby systems became unstable, so all related to the aerospace industry. So the Boeing video, which is available on YouTube, so if you type in what's next for Boeing, have a look at this video. It's quite interesting. It's very interesting. A redesign to an existing plane caused instabilities in the flight operation, and there was a few other issues, and it caused this plane sadly to lead to fatalities. So it's a very good video in terms of it, when you have issues in terms of design. So watch that, what's next for Boeing. This video as well, if you type in original footage of Leicester City helicopter crash, this here is when the helicopter sadly again spins out of control and causes fatalities, and that was due to sensors, poor information being fed back from the sensor to the control, so the control system wasn't operating effectively. And then another interesting one if you look at rotor imbalance. So in terms of the stability of a system, it's good to kind of take the mathematical approach initially and investigate the stability of the system via the closed loop transfer function that describes the closed loop control system. And if you, maybe for example, if you look at the Boeing, if they'd taken maybe a model-based design approach, not 100% sure if they did or didn't, but if they had, it might have enabled for kind of changes to be explored to the design, and then to find any potential issues further down the road. So if they change that, then what happens? So yeah, and not identifying potential issues can lead to instabilities and failure of the system, as you'll see hopefully if you watch these videos. So in terms of stability of a system, so here I've got here the pure discrete time equivalent of the sample data control system, where we've got a proportional control gain in the feed forward. Here's our continuous system. So not continuous system, it's been discretized. It's our continuous system here. Z transformation of this gives us G of Z, so our discrete time representation of the continuous system, which is effectively just capturing information at every sample point. Here we've got an ideal sensor, so we've got negative unity feedback, our reference, and the error is formed by the reference minus the measured output. So G subscript CL is our closed loop transfer function, and it's given by this equation here. So investigating system and control design via theory and simulation, as I said on the previous slide, what it enables us to do is to identify kind of any issue. So we can run what if scenarios, so we can put disturbances on the system and see how well in this case we've just got a proportional control gain, but how well the controller compensates for such disturbances, or maybe put some wear and tear on the system, vary maybe the reference that's going in, maybe put some noise on the sensor. So at the moment we're just looking at proportional control gain this week. Next couple of weeks we'll explore this a little bit further and also introduce an integral and derivative control. So all systems are pretty much, the aim of the closed loop control system is designed such that it remains stable. So you've got a system response that effectively ends up in steady state. You don't have a system response that grows. So just to recap you from the unit circle last week, so we've got the unit circle here. The jury test that I'm about to detail you is similar to the Ralph Herbert's approach. Okay, it's an algebraic test, and it effectively determines, in terms of the jury test, whether the roots of the polynomial. So the polynomial, what we're going to look at is the characteristic equation, and the denominator. When we equal that to 0, that's known as the characteristic equation. Effectively telling us whether the roots of that lie within the unit circle. Because if you remember from the last lecture, series of slides, your poles, if they're inside the unit circle, which has a modulus of 1, the system would, in fact, all the closed loop feedback control system we're looking at now, would be stable. Here on the unit circle, so if you had a modulus of 1 or a radius of 1 at your poles, then the system would be marginally stable, so you'd have a system response that continually oscillates, and outside the unit circle your system would be unstable. So as we increase the proportional control gain, when we looked at the continuous time domain and we looked at the S-plane, some particular systems, the poles potentially can move from the left half plane, which is stable, over the imaginary axis and into the right half of the S-plane. And that was for a particular type of system, which we won't go on to at this point. Now in the discrete time domain, a proportional control gain value, a certain value will move your poles outside of the unit circle. Hence, your system will become unstable. So it's important to, first of all, not just evaluate whether the system is stable or not, so looking at where the roots lie in the unit circle, which the jury test will tell us whether they do or not, but it's also important to determine the range in terms of what the KP value can be. So KP equals 0, which is your open loop poles, all the way up to a value that is going to move your poles to be on the imaginary axis, because that tells me that you want, well, when you work out that value or wherever it is, it'll tell you that effectively you want your poles to be within that range, or you want your KP value to be within that range so that your poles stay within the unit circle. So in terms of the jury test, it involves populating a table that looks something like this, and it's based, as I said, based on the characteristic equation coefficients. So here we've got a characteristic equation. You see it's equal to 0. Effectively, it's the denominator of the closed loop transfer function and equal to 0. So here we've just got a general form where an is greater than 0. So you can have a go at you could populate a an example characteristic equation here. I don't know, a0 z to the 4. I don't know if you want to look at n when n equals 4, where n is the order of the system. And you can kind of work your way through. I'm not going to spend too much time on this. I'll get you slightly familiar with it. So if you're looking at the table, you've got here your columns and here your row. The number of rows used is given by this. This is an important equation to remember. So if you had a fourth order, it would be 2 times 4, so 8 minus 3. So that tells us that the number of rows that you need to use is 5. So 1, 2, 3, 4, 5. So you'd have to use these rows, and you'll see how this populates as we go through the video. But you can already see if we had a fourth order, that'd be a. So 4, a to the n minus 1. So a 4 minus 1, a3, a2, and a1, and a0. As you move around, so you'd end up with 5 a's populated here. Just remember, a0 is a subscript 0 is greater than 0, and then likewise. This here, row 2, is effectively this row here, but flipped. So you've got A0, A1, A2, A3, and then A4. So A4, that, A3, that, A2, A1, A0. You then have these rows here, so row 3 and 4. You have to determine these using an equation that I'll show you in a minute. And also, in this case, row 5 here, row 5 ID. Again, there's another equation that you have to use. Well, once you've determined row 3, it's similar to rows 1 and 2. When you've determined these values, you effectively just flip the value round. And you'll see that. So these are the equations to use for rows 3 and 5, or rows, I should say, use equation 1.3 for rows 3 and 4, and equations 1, 4 for row 5. So here it's b subscript k, where k is these integer terms, 1, 2, 0, 1, 2, 3, 4, n minus 1. You'll understand what this k value is in a little while. Okay, just park that for now. But it's effectively equal to the determinant of an a0, which is here. So these values here, whatever you use, whatever b k ends up being, you always use these two values here. And then an minus 1 minus k. The order change is fixed. So if you're looking at a fourth order, so it'll be 4 minus 1 minus k. But like you're going to see in a minute, k can effectively change. And then here k plus 1, where again k could change. So these two values here are going to change because they're going to change the location of the values that you populate this 2 by 2 with. So this is b subscript k is equal to the determinant of this here, this 2 by 2, which is effectively equal to that, the an minus a k plus 1, take away a0, multiply by an minus 1 minus k. And then again, exactly the same pattern for k0. So you can see these two values here, you populate them from here, and again, these two are going to change as a function of this k changing. So the table, what you're going to be able to do to begin with is populate, well, given that you've got a characteristic equation of at least, well, if it's second order, you'll only use the first row, because if we go back to the equation here, 2 times 2 minus 3, so you just end up with that equaling 1, so you don't use the first row. So for second order, you don't use the first row. For a third order, you use the 3 rows, and then for a fourth order, you use the 5 rows. And this following are necessary and sufficient conditions for a stable system. So once you've populated the table, these are criteria that you need to run through. And how I would advise you do it is I'd fill out, first of all, if you've got a third order, I'd fill out rows 1 and 2 to begin with. Because what happens if you don't meet one of these criteria, say for example, if I don't satisfy this criteria here, you stop, okay? Because you know that is telling you if you don't satisfy it, you know that your system is unstable, and hence you've got poles or a pole outside of the unit circle. So I'd run through, to begin with, I would just do the first 3 here that don't require anything other than the first row being populated, which the second row is populated based on the first row anyway. So the first 3 criteria, so the modulus of an, so here is less than a0, which is the value here. So if you satisfy that, then you are, well, the aim is to satisfy that and meet that criteria. And if you do, move to the next one. So what this one involves is taking the polynomial and replacing all the z's with 1, and if the product of that is greater than 0, you meet that criteria and it's satisfied. Rule 3 is, this very much depends on the order of the system, so whether you've got even, whether the order is even or odd. If it's even, then when you replace all the z's with minus 1, the product of that must be greater than 0. When it's odd, so you replace all the z's with minus 1, it must be less than 0. Alright, so first of all, you run through these 3 criteria, and then what you'll have to do is, depending on the order of the system, so if it's third order, you'd have to just do this formula here, because you would only go down as far as this on the table. If it's fifth order, then you would, well, you'd only go this far, but if it's fifth order, then you would then go down to row 5. So then what these conditions say is the modulus of bn minus 1, so here, must be greater than the modulus of b0 here. If you satisfy that, then you know, if you've got a third order and you satisfy that, you know your system is stable. If you've got a fourth order and you go about this, so the modulus of Cn minus 2 is greater than the modulus of C0, and you satisfy that, you know that your system is, in fact, again, stable. So what I've got now is an example to run you through. So the characteristic equation of a feedback control system is given by this. This is effective here as your fourth order polynomial. So in the general form, the equation is given by this. So just to help you, I've just highlighted A0, which is 1, A1, which is minus 1.2, A2, which is 0.07, A3, which is 0.3, and A4, which is minus 0.08. And you can see here that I've put them down here. Again, as I've iterated, you need to work out how many rows you need, and by now you've probably just remembered how many rows you need for a second, third, and fourth order. But for a fourth order, it's 2n, so 8 minus 3, so it's 5 rows. And straight away you can see how I've populated the table here. So A4, A3, A2, A1, A0. And as I told you, the values effectively here flip. So you can see A0, A1, A2, A3, and A4. So that's me populating the first 2 rows. What I'm now going to do is run through the first 3 checks, that first 3 necessary and sufficient conditions for a stable system. So if I remember here, the first test here in red, so modulus of an must be less than must be less than a0. So in this case, an, which is a4, is equal to 0.08, and a1 is 0. So that's obviously less than 1. So first condition is satisfied. And then if you remember the second condition here, whereby I effectively just replaced all the z terms by 1. So you can see here I've put p 1 and then replaced all the z terms with 1, and then worked out the product to be 0.09, which in this case is greater than 0. So the second condition again is satisfied. If I then move on to the third case, in this case remember that we've got an even number here in terms of the order, even, so it means that the product of, when I effectively replace everything, when I put a minus 1 into all the z's, this must be greater than 0. So you can see I've done that here. So I've put minus 1 into all these, and I've worked out the value here is 1.99, which in this case is greater than 0. So again, this third, another condition, in this case is the third condition is satisfied. We're now going to work out rows 3 and 4 initially, what the coefficients are in here. You'll see it's already populated and the calculations are up here. So using equation 1, 3, that was earlier in the lecture, you should remember this equation where I told you that at that point in time not to worry too much about the k, because I'll now explain to you where it comes from. So bn minus 1, where n is the ordered system, so in this case n is 4. So b4 minus 1 is equal to 3, so b3. bk is effectively equal to this value here. So in this case, bk is equal to b3. Okay, so k is equal to 3. So then when you're looking at this formula here, we know an, a0 are these two terms here. And then an minus 1, so a4 minus 1 minus k. We've just worked out k to be 3. So we know that that's going to be 4 minus 1 minus 3, so that's going to be a0. And if you look here, this ak plus 1, so we worked out k to be 3, so it's going to be a4. So then if we're looking here at the table, so we worked out that this is a0, so effectively a0 here, 1, and a4 here, or you could take the a4 from here, or a0 from here. So you can see these coefficients here. And then if we're doing the same for, then we've just worked out for B3, then we need to work out for B2, B1 and B0. So if you look here, Bn minus 2 is equal to effectively B2, therefore K is equal to 2. So if we populate this here, so it's going to be, again, A is going to be the same coefficients up here for A4 and A0. And in this case, it's going to be A4 minus 1 minus 2, because in this case, K here is equal to 2. So it's going to be A1. In this case, A2 plus 1, so it's going to be A3. So again, if you just look at the table, A3 here, and then if you recall, this one was A1, so minus 1.2. And I'll run through one more. So in this case, we work out as B1, so therefore K is 1. So B4 minus 1 minus K, in this case K is 1. So that's going to be A2. So here, 0.07. And then A1 plus, or sorry, I should say AK, where K is 1, plus 1, which is A2, which is here or here. Okay, so then the pattern follows for B0, but I'll not run through that one. So now what we need to do is work out the determinant of these four here. So it's effectively the determinant is equal to AN minus AK plus 1, take away A0, multiply by AN minus 1 minus K for all these. So you can see here how these are then worked out. So let's multiply by this. 0.0064, take away 1 and work out the value. And likewise for this one, 0.01 multiply by 0.3, so that's the product. Take away minus 1.2 multiply by 1, so you end up with plus 1.2. Okay, you do that for all them. And then you can see then we've populated here the values for B3, B2, B1, B0, and as I said at the beginning, you can see that the values then populated basically reversed. System. Now we're going to determine the values, the coefficients in row ID 5. So we use this equation 1, 4 that we saw earlier, and it's exactly the same idea as we saw on the previous slide, where Bn minus 1, here B0, and then these two coefficients here that make up this 2 by 2 are determined based on a function of K, where K we determine in the same manner that we did before. So here you can see for what we need to determine now is C2, C1 and C0. So here's C2, C1, C0, and you can see them and exactly the way. So in this case C2 where K is 2, C1, K is 1, C0 where K is 0. So in this case, if we're looking at these as an example where K is 2, you can see the value. Here where K is 2 again, and then here we're obviously looking at B0, and here we're looking at B3. So B0 and B3. So the pattern follows on all the way through, so I'm not going to spend any more time doing that. But the same idea, so you work out the determinant. So this multiply this, take away this value here, multiply this value, and the same, so determinant of this value here, multiply this value, take away this value, multiply this value, and then you work out the three values, populate them into the table here, and then you've got your completed jury table. So then the final step of this question to do is then just to see if you meet the fourth necessary and sufficient condition for a stable system. So if you remember this, the modulus of Bn minus 1 must be greater than B0. So Bn minus 1, which in this case is B3, which the modulus that is 0.9936, must be greater than B0, which in this case B0, modulus that is 0.2040. So in that case, we satisfy that, so yeah, that's okay. And then moving on to this one, that one you only consider if you've got a system of third order. This one we consider when we've got a system of fourth order, which in this case we have, and hence we get 5 rows, so that's why we concentrate on it. So C2 minus 1, which is C2, so the modulus of that is given by 0.9456, and that must be greater than C0, which in this case is 0.3150. So you can see that's the case. So you can see the fourth and final condition, which must be necessary and sufficient, is met. Hence, the feedback control system, in this case with the proportional control gain, well, whatever it is, we're not sure, is satisfied, and it gives us a stable system. So that's demonstrated using the populating the table, and then showing where we must meet the sufficient and necessary condition for a system to be stable. What we have here is a further example where we've got the characteristic equation, but what we have is this unknown Kp value. So if you remember, I told you at the start, we had Kp is equal to 0 if you're open loop poles, and as you increase your Kp value from 0 to infinity, at some point the K value will result in your poles moving outside of the unit circle. So what we're looking at in this particular question is determine a range of values for Kp which the system is stable. So effectively, what value of Kp will keep the poles within the unit circle, and just note that the controller gain Kp must be greater than 0. So here you can see I've determined the coefficients. A0 is 1, A1 is minus 1.5, A2 is Kp plus 1, and A3 is minus 0.25. Note, if we're in this rule, 2 multiplied by 3, which is 6, minus 3, hence you need to use 3 rows in the table. Okay, so what we're going to do now is check the first 3 necessary conditions. So in this case, remember this condition, so AN, the modulus of AN must be less than A0. So AN, which in this case is A3, so 0.25, must be less than A0, which A0 is equal to 1. So the first condition is satisfied, because that is. In this case, replace for condition 2, replace all the z's here with 1. And what you'll notice is that for this system, for the second condition to be satisfied, Kp must be greater than 0. And the third condition to be satisfied, so in this case we've got an odd number, so when you replace all the z's with minus 1, it must be less than 0. And then if you look at this, then this equation we end up with, effectively it would be satisfied if Kp was greater than 0. Okay, so in both cases we know that Kp value greater than 0 would end up with meeting the condition. And then the third row, so now we're going to populate the third row. So it's exactly the same manner in the previous video, so we're just using equation 1, 3, and you can see here I've populated the table. Okay, so notice we've got 1, 2, 3, 4, and then 1, 2, 3, 4. Okay, and obviously these here have been populated, they effectively just reverse. And then here you can see now we've got 3 unknowns, so B2, B1, and B0. So the equations here are the same manner, so B2, B1, B0, where in this case K is 2, K is 1, K is 0. Work out these, so as obviously K is 2, so 2, 2. So that's going to correspond to A0, A3, A1, A2, and so forth. Then populate these and then work out the determinants as we've done so before. So these two multiplied, take away these two multiplied, give you this value. This multiplied by this, then take away 1 multiplied by minus 1.5, give you this, and then likewise. And then what we've got is these 3 values that you can see I put into the table. We've got this unknown Kp value. So the fourth condition, we only consider the one associated to the row 3, and the modulus of Bn minus 1 must be greater than B0 for it to be satisfied. So for this to be satisfied, what you see is I've put in the value, so B b in this case is b2, because bn where n is 3, minus 1, so it's b2, put that in there, and that must be greater than, in this case, if we're looking at b0, so 0.375 take away kp plus 1. Okay, so then what I've done is, here I've just taken away the 1, so then you end up with this, so take away the 1, so it's going to end up with minus 0.625. And then what I'm doing is when I'm looking at that, I'm thinking, right, how is this here, what kp value is going to ensure that this value here is greater, this value here is greater than this. And a kp value of less than 0.3125 here will result in a value that is effectively less than this. Okay, so 0.325, a value less than that will result in a value being smaller than this, hence you would satisfy the condition. So what that tells us then is then the kp value must be greater than 0, and it must be less than, a kp value must be less than 0.3125 for the system to satisfy the condition of the system to be stable. So what I've got here is 2 exercises for you to have a go at. So exercise 1, similar to the first example that we had, to determine the stability of the stability condition of the following characteristic equation. So here you've got a third order, so have a go at that. Exercise 2, you've got a characteristic equation that's given by this, where you've got an unknown kp value, where kp is your controller gain, kp must be greater than 0. Determine the range for which the system is stable. So pause the video and have a go at these examples, and they're very similar to the 2 previous, so use them as a benchmark. So in summary, I hope you understand the importance of system stability. So the idea of developing a mathematical model and perhaps following a model-based design approach such that you can test it in different scenarios and see at which point it perhaps becomes unstable, and you can design around such occurrences. And you understand how the theory in the z-plane corresponds to stability. Okay, that's been detailed. So inside the unit circle will give you a stable system if your poles are located within the unit circle. The jury test, so if we do create a feedback control system, if we've got a transfer function feedback control system, we can undergo the jury test to determine whether the system is stable or not. So I populate the jury table and then following the necessary and sufficient conditions to see if the system is effectively stable. And just remember, if at any point you don't meet a condition, stop there, because your system is in fact unstable. And then finally, rather than just working out whether the system is stable or not, we can work out the range of kp values that will result in a system being stable. So we know that in a particular case, in a control system, we can't go over a certain kp value because it will result in our control system going unstable. Okay, hence moving the poles outside the unit circle when we're looking at the theory. And what we'll do next, in the next lecture, is we'll look at the root locus, where that looks at the path of, effectively, when you change in the kp and the path of the poles on the unit circle. So I hope if we're looking at the key learning points, you're able to explain the method behind the jury test for the evaluation of system stability and how to undertake the test, and also explain the process of determining an unknown proportional control gain to give a stable system and how to undertake the steps. So I hope you've enjoyed the video. If you've got any questions, then please contact me. Thank you.